All right, let's get right into it. Today, we're going to talk about what makes or breaks the quality of fixation in histopathology. Now, there are a bunch of factors to think about, but the good news is most of them are actually pretty easy to control once you know what you're doing. And trust me, getting this part right from the start, is absolutely non-negotiable. And this quote right here, this is the core message, the one thing you have to remember. I love the analogy of building a house. Fixation is your foundation. If that foundation is weak or cracked, it doesn't matter how great the rest of the house is, it's all going to be compromised. It's exactly the same in the lab. A bad fixation is an error you can't undo. It messes with everything that comes after, processing, staining, and yep, even the final diagnosis. So here's our game plan for this explainer. We're going to cover the fundamental physical factors, the critical role time plays, how to choose your fixative wisely, how fixatives actually get in and do their job, and then we'll wrap up with environment, storage, and that one final non-negotiable message. All right, first up, the fundamental physical factors. We're talking about temperature, size, and volume. You've got to get these three things right because they really do set you up for success or failure. So let's start with temperature. This one's a real balancing act. If you crank up the heat, sure, fixation happens faster, but you also speed up autolysis, the tissue's starting to break itself down, and other stuff starts leaking out. So what about going cold? Well, fixing at 0 to 4 degrees Celsius slows down all that breakdown, which is why it's great for things like electron microscopy. The catch? You might lose some of those super fine details. That's why, honestly, a lot of labs just stick with room temperature. It tends to give the best overall preservation. But if you're in a hurry, you can go warm, up to 45 degrees Celsius. Think tissue processors or microwaves. It's faster and generally safe, as long as you don't go over 45 degrees. So let's just quickly recap that. At 0 to 4 degrees Celsius, you get slower fixation, which means less tissue breakdown, but you might miss those fine details. Then you got room temp, which is really that sweet spot, offering a great balance for better preservation. And finally, going up to 45 degrees Celsius gets your faster fixation, and it's safe as long as you don't overheat it. It's all about picking the right tool for the job. Okay, next up is tissue size. And this is a huge one. Why? It's all about penetration. The fixative has to physically soak into the tissue to do its job. If your sample is too thick, the fixative just can't get to the middle, and that center part is going to start to autolyze. It'll just break down. Think about large organs, like a colon. You have to, and I mean have to, open them up before you put them in fixative. If you don't, the fixative won't touch that inner lining, and it'll basically rot from the inside out. For your routine sections, the hard and fast rule is no more than 3 millimeters thick. That ensures all the reagents can get in. And here's a little tip. If you're on a fast processing schedule, go even thinner. A good rule of thumb I always use is that the tissue inside a cassette should never, ever touch both sides. So let's put that into a simple checklist. For large organs like an intestine, what do? You open them up before fixation. For your small routine samples, you cut them into pieces that are 3 millimeters thick or less. If you're using a short or fast protocol, you'll want to cut them even thinner. And when you're loading the cassette, just make sure that tissue isn't touching both sides. Easy. And that brings us to our third physical factor, volume. The magic number here is 15 to 20 times. That's right, you need at least 15 to 20 times more fixative volume than your tissue volume. So why on earth do you need so much? Well, it comes down to what we call a two-way exchange. Think of it this way. As the fixative binds to the tissue, it's getting used up, right? So the solution gets weaker and weaker. At the same time, the tissue is releasing its own stuff, like salts, back into the fixative, which also messes with its strength. So if you don't have enough fixative to begin with, it gets diluted and weakened so fast that you end up with incomplete fixation. And that leads to, you guessed it, terrible staining and results you just can't trust. Okay, let's switch gears and talk about our second big topic, the critical role of time. How long you leave a tissue in fixative is every bit as important as temperature or size. Go too short or too long, and you can seriously mess up the tissue structure, the staining, and especially your IHC results. So, what's the magic window? For most specimens in 10% NBF, you're looking at 6 to 24 hours at room temperature. Now, if you've got smaller biopsies, 4 to 6 hours might be perfectly fine. But for bigger stuff, like a colon section, you might need to go longer, maybe 24 to 48 hours. And why is this range so great? Because it gives the fixative enough time to fully penetrate and create all those protein crosslinks. This is what stops autolysis in its tracks, keeps the cell structure looking great, and sets you up for beautiful, accurate staining. And getting this timing wrong, well, the consequences are pretty bad. Let's talk about under-fixation. That means you get incomplete cross-linking, which leads to autolysis, a smudgy look, and really poor stain uptake. On the flip side, with over-fixation, you have excessive cross-linking. This makes the tissue hard and brittle, a total nightmare to cut, and it can mask the antigens you need to see for IHC, which is a disaster. So this table really lays it all out. If your fixation time is too short, let's say less than 6 hours, the tissue effect is autolysis and distortion. The staining impact, it's going to be patchy and weak. And your IHC result, you're looking at antigen degradation and false negatives. Now, let's jump to the other extreme. Too long, over 48 hours. The tissue becomes hard, brittle, and shrunken. The stain penetrates poorly and looks pale. And for IHC, you get antigen masking, which leads to, you guessed it, false negatives. It's only in that optimal 6 to 24-hour window that you get that beautifully preserved morphology, clear, even staining, and reliable antigen detection. It's so important to hit that sweet spot. All right, on to our third section, choosing your fixative wisely. And this is a big one because it is definitely not a one-size-fits-all deal. You've really got to think ahead about what tests are going to be run on that tissue because choosing the wrong fixative can be an irreversible mistake. So let's start with a basic question. Is fixation always necessary? And the answer is nope. For things like immunofluorescence or certain enzyme studies, you actually don't fix the tissue at all. You just freeze it. And some IHC tests also need either unfixed tissue or tissue that's been fixed really fast with something like acetone. But for most histology, it's all about picking the right fixative for the job. For example, if you want to see missile striations really well with a PTH stain, Zenker solution is what you want to use. If you need a beautiful trichrome stain, Bouin's solution is your best friend. And sometimes you can even use a second fixative after the first one. This is called post-fixation or mordanting. A classic example is hitting a formalin-fixed tissue with Bouin's before doing a Mason trichrome stain to really make those colors pop. And here is a serious warning, because the wrong fixative can literally lead to a missed diagnosis. I am not exaggerating. For instance, to diagnose a pheochromocytosoma, you need to see chromophin granules. Well, guess what? Formalin completely destroys them. You have to use a dichromate fixative like Ort's solution. Another perfect example, urate crystals in a gout specimen. They will just dissolve in any water-based fixative, so you have to use absolute alcohol. These aren't just minor mistakes. They are the difference between getting a diagnosis and having nothing to show the pathologist. Okay, on to our next section, fixative penetration and action. So now we're going to look at how these chemicals actually get into the tissue and what they do once they're there. This is a really cool distinction to understand. You have coagulant fixatives like alcohols. They work by pretty much clumping proteins together as soon as they get inside. Then you have non-coagulant fixatives like formaldehyde. Now, formaldehyde gets into the tissue really fast, but it works slowly, forming all those protein crosslinks over time. So the big takeaway here is that fast penetration doesn't automatically mean fast fixation. And just to give you an idea of penetration speed, here's a quick ranking. Number 1, the fastest is formaldehyde. Then comes acetic acid, followed by mercuric chloride, then methyl alcohol, osmium tetroxide, and finally, the slowest one on this list is picric acid. All right, we're in the home stretch. Let's talk about the last set of factors, the environment, storage, and those final steps. Let's tackle storage first. You can keep formalin-fixed tissue in formalin pretty much forever. But, and this is a big but, if you think you might need to do IHC down the road, you should move that tissue into 70% alcohol after it's done fixing. Why? Because that stops the cross-linking and helps preserve the antigens. Okay, now for pH. For regular light microscopy, you don't have to be super precise. Anywhere from pH 4 to 9 is usually okay. Just be aware that a really low pH can create formalin pigment. But for electron microscopy, oh, it's a different story. The pH has to be spot on, buffered to a physiological pH between 7.2 and 7.4, or you'll wreck the cell's internal structures. Okay, let's talk osmolality. That's just a fancy word for the concentration of stuff dissolved in your liquid. You've got 3 scenarios. Isotonic is when the concentration is the same as the cell. That's good. Hypertonic is when the fixative is more concentrated and it sucks water out of the cell, making it shrink. And hypotonic is when the fixative is less concentrated, so water rushes into the cell, making it swell up and maybe even burst. So how do we prevent that? A simple trick is to add some harmless salts to your fixative to balance things out. And what about short-term storage if you can't fix it immediately? The key is, do not soak it in saline. Instead, put it on some saline-dampened gauze and pop it on ice. And for very specific things like kidney biopsies, you'll want to use a special solution called Michel's. And that brings us right back to where we started, with this one non-negotiable message. The quality of your fixation is absolutely critical. It is the foundation for everything else you do. You cannot fix a bad fixation. Any mistake you make right at the beginning will ripple through every single step that follows, affecting your staining, your interpretation, and at the end of the day, the diagnosis you give to a patient. So get it right the first time.